So the comparison test, and this is actually something that Avi had asked about earlier, which is, I think it was Avi. Yeah, which was, can we just go straight to comparing to a comparison test? And at that time, we did not have a series comparison test. We only had integral comparison tests. But now here's the, what do we call it? The analog to the integral comparison test is a series comparison test. There are actually two series comparison tests, and they're both powerful in their own right. So this section contains two, count them up, two new tests. The first one is going to be very familiar. It's called a series comparison test. Suppose we have two series, the series A sub n and the series B sub n, with an order to the sequence terms. That is, both of the sequence have terms that are positive, so that's critical. Both sequences that the series are based upon are positive. They don't always have to be positive. It's just positive from some value onward. They have to be positive basically at the tail. Okay. So we have two sequences that build a series, and both sequences are positive. Not only that, but there's one sequence that's above the other. So let's just say that B sub n is greater than or equal to A sub n, and they're both positive. Okay. Well then, if the summation of B sub n is finite, in other words, if you add up all these terms and it becomes something finite, well, because A sub n is less than that, well, then adding up all the terms of A sub n should be finite as well. That is the same thing as the comparison test for integrals, right? The same exact idea. All right. And likewise, if you know that the area, not the area, but the terms, if you add up all these terms right here, A sub n's, and they blow up to infinity, well, because B sub n is bigger than each of those terms, when you add up all of B sub n, they'll blow up to infinity as well. So if the summation A sub n is divergent, so is the summation B sub n. Summary of this really is this, what the way to say this is this. Convergence above implies convergence below. And I wrote it that way when we did the integral comparison test. And then divergence below implies divergence above. That's, I think, just the easier way of saying it. It's really kind of clean, easy to understand. So anyhow, those are really good ones. I think what I'll do, because we just have 10 minutes and I want to showcase how these work, I'm going to skip the proof for right now. I do know this proof pretty well, but I'm going to go ahead and skip it for right now and just do an example. So determine if the following series is convergent or divergent. Again, you do not have to stick with the section that you're in. Don't just think, well, I'm in the comparison test section, so let me always use that. Start by doing something easy like a divergence test if you think this is divergent, which it's not. But if you wanted to try, you could. Divergence test. Well, I can tell you right now, the limit as n goes to infinity of our base sequence is 0. So therefore, divergence test is inconclusive. Okay. And let's see, it's not geometric. I'm just going to write that in here. It's not geometric, even though there is actually a term in the denominator that is raised to a power n. To be geometric, the entire thing, the entire sequence term has to be raised to the nth power. And that's not what we have here. So it's definitely not geometric. It's not going to be telescoping. I can easily see that as well. That's a rare gift if you have a telescoping sequence. Those two in red right there, the geometric and telescoping, those are the only two of all of the series that you can actually figure out what they sum up to. the infinite sums are. Well, what are you going to do? Let's see. So we pretty much have gone through all our possible tests. It's not, by the way, a P series, right? It's not of the form 1 over n to the p. So we can't do that. So, and by the way, you may say, well, let's see, can we do the integral test? If you want to integrate 1 over 3 to the x plus x, be my guest. I don't want to. I'll put it in green. I'll say we could use integral test, but it's a hard integral. It's a hard integral. If you like to integrate, and I love to integrate, then go ahead and try to integrate 1 over 3 to the x plus x. It doesn't work very nicely. So instead, I'm going to try to do a comparison. I'm going to try to compare to an easier series. So let's build a comparison. Now, to build a comparison, my strong recommendation is to look for the most powerful term in both the numerator and the denominator. I've said that when we were doing the comparison test for integrals as well. So that should make sense. So I'm going to go ahead and say, so let me actually make that little note. Look for most powerful term in numerator in top and bottom, I'll just say. And I tend to start with denominators. So I'll just go ahead and look at the denominator, 3 to the n versus 3 to the n plus n, right? So those are the denominators there. The original denominators on the right, and what I want to compare it to is on the left. Notice here that 3 to the n is definitely less than 3 to the n plus n. That should make sense. Taking the reciprocal of both sides, 1 over 3 to the nth, well, that's greater than, you flip the inequality when you do a reciprocal, it's greater than 1 over 3 to the nth plus n. And by the way, that's positive there. So if I could showcase that the summation of that sequence is convergent, then the summation of this sequence by the comparison test will be convergent. It's technically called the series comparison test. So let's go ahead and look at the summation. So consider the summation n equals 0 to infinity. They started at 0, so I'm starting at 0. However, remember, I could lop off the first 3 billion terms if I wanted to. If you want to start at 1, you're more than welcome to start at 1. It doesn't actually matter. But I'm starting at 0 just because I want to. 1 over 3 to the n. It's the same thing as the summation from 0 to infinity of 1 over 3 to the nth power. That is geometric with a common ratio in magnitude less than 1. So I'll say it's geometric and convergent because 1/3, the absolute value of it, is less than 1. So we happen to know that that series that we're comparing to is going to converge. By the theorem, hopping back to series comparison test, I have two series, the original and our brand new one, where our original sequence is less than our brand new sequence, and we have proven that our brand new sequence is convergent, or brand series, our series, brand new series is convergent. And remember, convergence from above implies convergence below. So thus, our series that's below our new series must also be convergent. So let me just go ahead and say, thus, the summation, what was it? 1 over, I guess, 3 to the n plus n, and I think we're going from 0 to infinity, is convergent by the series comparison test. And there are so many different, well, there's not so many, but there's 3 different comparison tests. So it's important that you note which one you're talking about. So that's why I'm saying the series comparison test here. And just to shorthand it, we call that the SCT. Now, I did a lot of talking during that, but the reality is it's very fast to do this. If I see this, I just think, okay, it's not geometric. I know it's the divergence test not going to apply, and I don't want to integrate that. So I'm going to compare. And I'm immediately within 10 seconds already to this inequality. I know 3 to the nth is less than 3 to the n plus n. Take the reciprocal. And now I know here's my original series sequence. Here's my new sequence that I'm comparing it to. And I know that if I add up 1 over 3 to the nth, which is 1/3 to the nth, I know that will converge. Thus, the series of 1 over 3 to the nth plus n will also converge by the series comparison test. There you go. It's very, very nice. So the series comparison test is actually a pretty nice one to get used to. We don't have enough time for another problem. So, but to give you a heads up of where we'll be at the end of next class, we will have this brand new tests so far, and it'll just keep growing. It just gets bigger and bigger. So by the time we get through this, we'll have probably let's see, we'll have alternating series, we'll have absolute convergence, we'll have ratio and root. So we'll at least have 4, if not 8 more lines to this. So it does get kind of large, but that's why I summarize at the end of every class. Here's where we're at. Main thing to note here is with what we're dealing with right now, the series that we can work with are either geometric or have positive terms. That's what's important. All right. So that ends the discussion for today. Sorry about that proof earlier. I'll try to hammer that out and see if I can maybe record something for you guys. And I'll be in my office hours in 10 minutes. Otherwise, if you're not there, I wish you a wonderful Monday. Enjoy your day. And go ahead and get started on the homework. I'll fix that problem number 4 during break here. And I'll be back in 10 minutes. See you then. Take care.